a geometric picture for pattern formation, and I would like to start with a short recap, a kind of a summary of the main uh, ideas and main concepts that we found yesterday. And for those who are not familiar with terminology in bifurcation theory, here is a short reminder of what the terminology is. So you talk about bifurcations if the order parameter as a function of a control parameter, say the amplitude of a pattern as a function of protein concentration, changes in a abrupt qualitative way. There's two types I will talk about quite a bit. One type of bifurcation is called a saddle node bifurcation, where out of the blue you have the emergence of a stable and an unstable branch of a pattern or order parameter, and the pitchfork bifurcation, where you first have one stable fixed point and then after a threshold value of the order parameter you have two stable branches emerging and one unstable branch emerging. If you like, you can compare this with a second order phase transition and that with a first order type of phase transition. So you go from a continuous change in order parameter to a discontinuous change in order parameter. This is called supercritical, this is called subcritical, if you like. The generic case, the one which you find typically, is this one. For that you need a special symmetry, you need to fine-tune, so you only find it at special places in parameter space. So let me start with what we learned about these equations. So we were discussing a set of very simple equations for two components, the membrane component and the cytosolic component, such that the overall mass in the system, so as you integrate from 0 to x, the sum of m and c, this equals a constant, and the boundary conditions were that at the boundaries left and right there were no fluxes coming in or out of the system, so the gradients of m and the gradients of c are 0 at those boundaries. Now the point I was trying to make is that in order to understand such a set of equations, and I by purpose picked the simplest possible case, you can actually understand that equation by mapping or relating behavior in phase space and real space. So let me plot this again. Here we have phase space with one axis being the membrane concentration and the other one being the cytosolic concentration. And then here I plot the real space. So for example, the membrane concentration as a function of position. The goal was to learn from the geometry of phase space in order to understand what the pattern actually is. Now to that end you needed several characteristic lines that you need to consider. One characteristic line in the phase space is simply the simplices, where the density, the overall density of the protein is constant and divides up into different fractions of membrane concentration and cytosolic concentration. I called this here the reactive phase spaces. And there's a whole set of them. As you vary n, these simplices move up and down, And you can think of this as local phase spaces because the value of the density may just depend on where you are in your system. So again, think of this as compartments, where each compartment corresponds to a certain position in space. Then this amounts into a distribution of mass, and this distribution of mass is the set of reactive phase spaces you have in the phase space. Okay, the second geometric object that was quite crucial in understanding pattern formation is what is the chemical equilibrium in those systems. So for that, you needed to look at these equations. When are they stationary without diffusion? Well, they are stationary if the reaction terms are exactly 0. So F equal to 0, and those define the equilibria, and the terminology of non dynamics is to call these lines here null lines. And let me draw one of those null lines. Okay, so like so. This is my null line defined by F identical to 0. And this particular point here is a special equilibrium corresponding to a particular value in the density. All right, and we had a set of criteria. And the first one of these geometric criteria is when you have a locally stable fixed point. So question was, how do you figure out when a compartment, so a local point x along your one-dimensional line is stable to perturbations or not? And what I showed you is that this has a condition that the slope of the null line, and I hope I wrote this down, so chi of n is the slope of the null line at the reactive phase space n. This slope of the null line had to be such that it is actually less steep than the reactive phase space. So here the orange curve is less steep than the yellow curve, and then this fixed point here is locally stable. So here, that particular case, you have a stable equilibrium according to the geometric condition I wrote down here. Okay. All right. Next, we asked ourselves, well, what about lateral stability? And when does the system equilibrate towards a stationary pattern? And I showed you that that's the case in the flux balance subspace. So this flux balance subspace was given by the condition that the gradients of the membrane density times the diffusion constant, so the diffusive flux on the membrane and the diffusive flux in the cytosol, they are equal and opposite. And this condition then gave rise to another geometric object, the flux balance subspace, which has a slope that's minus dm over dc. And what we, so in there, the final stationary pattern has to reside. It has no option. That's where it needs to go. And if you like, you can call this flux balance subspace a attractor, and that means the geometric object that you find in phase space towards which the pattern converges in the limit time going to infinity. The attractor here then corresponds to the pattern in the real space. All right. And now how do we construct the patterns? Well, I forgot to mention the condition here for lateral stability. And here what you mean is, if you think of two compartments, when is the system stable or unstable towards exchange of proteins, particles between those different compartments? So stable towards diffusion or exchange between the compartments. And the condition for that also was a condition on the slope of the null-cline. The condition was that the slope of the null-cline, so this one here, needs to be steeper than the slope of the reactive phase space to be unstable. And here I wrote down the condition for stability. So if the slope is greater than minus, then that slope, you have lateral stability. Okay. All right. What else? Then we have all the geometric objects in phase space available. And once we have those geometric objects available, there are special points now in that phase space, and we call them landmark points. Those landmark points here are the intersection points of the null-cline and the flux balance subspace. So those points here, which are indicated in green, they are called landmark points. And the name I choose, or we choose, because they help us to infer the pattern on the right-hand side. So let me draw the corresponding values. So here, this is then M minus, that here is M plus, and this intersection point is M0. And corresponding to all these values of mass, there's of course also a corresponding value of the density, so N minus, N0, and N plus, corresponding to the respective reactive phase spaces, which I would draw through those crosses here. But don't draw this, otherwise I'm overloading the picture. Yeah, go ahead. Yeah. Doesn't have to be. They help me construct the pattern. I will talk about what the patterns will be. The intersection of all the 3 points need to be part of the pattern in a particular case, which is the limit that the system size goes to infinity. Yeah. There's no violation of that constraint. Well, this flux balance subspace has a distribution of mass, right? This is important. It's not that the mass is now homogeneous. Everywhere in space, you have a different value of the mass. So there will be a value of the mass n minus here, n naught here, and n plus there, and anything in between. And the constraint that you have here says, if you integrate over that, so the whole density here, so n of x and t, that needs to be n bar. And I'll use this condition later on to define where the position of the interface in the pattern actually is. All right? Now, let's go on here and use the landmark points to construct the pattern. So let me draw here these landmark points. One is M minus, the other one is M plus, and the third one is M0. And let me this here, dashed. All right. Now m minus and m plus are special points in two ways. Here in this graph, they have no curvature. Because f is 0, the stationary state, the curvatures need to vanish. At the left and right boundary, so at 0 and L, the conditions I have is that the gradients are 0. All right? And that's not necessarily meaning that the curvature is 0. But if you have gradients being 0, and you make those be at infinity, you will necessarily also have the second derivative being 0. So let me draw the pattern here in that limit. So in that limit, then you will have here a plateau and there a plateau. So meaning you have both the first and second derivative vanishing. And then these two endpoints, so that guy here and that guy here, they correspond to the plateaus to the right and left side of the pattern. And let me call these values m minus and m plus scaffolds of the pattern. So scaffolds for the plateaus, because in the actual system I'm not right at those points. I will be somewhere inside, as the second derivative will not vanish generically. So that means m0 and ml are not identical to m minus or m plus, but they will be close to it. So they act as scaffolds determining where the plateau of the pattern needs to be. All right, then I have a third point here, which is again an intersection point between the flux balance subspace and the nullcline. Again, f is 0. F being 0 means the curvature is 0. So I need to have an inflection point here. Okay. So at that point, there needs to be some kind of inflection point. Let me draw it. Hope I get it right. So here, at this point x0, you have a inflection point. And this is this point here indicated by m0. All right, so that's the basic picture I try to convey to you about pattern formation in such a system. And well, what you can kind of learn from that is the way you can think about a pattern is now in terms of a coarsened description. And the coarsened description now is in terms of regions. And as you read from here, from this pattern, there's 3 regions. There's one plateau region on the left. There is the interface. And there is the plateau region on the right. And they are very distinct. Yeah?
Sorry if this is obvious, but number of intersection points between the red and the orange line then determines how many constraints you have on certain values of the curvature, right? So we know, for instance, because of that it couldn't first go up and then down in the middle. So from the proposed.
Well, one thing I took for granted in the whole analysis is that I'm jumping from the initial flat pattern to the final steady state pattern. In between, as you saw from the simulation, there could be mountains and valleys, but they coarsen, and in the end you have this particular pattern. The shape of the nullcline and the relation to the flux balance subspace, that will teach us about what type of patterns I have, and I come to that. And if I don't answer your question, please ask me again. All right? Other questions? Yeah? Okay, that's yeah, the offset, so of that is determined by another condition. So let me maybe write it here. So eta 0, and let me call this eta 0 infinity in the limit where I do have an infinite size system. Then there's one condition saying that overall, as I'm not producing particles nor destroying them, the integral over all the reactions needs to be 0. So if I write that as an integral from m minus to m plus over dm, and then f tilde of m and eta 0 infinity. So remember what I did there, I transformed my variables to m and a set of variables orthogonal to the flux balance subspace. That integral needs to be 0. And as you can see from that relation, it actually does not depend on L. It neither does depend on the number of particles n bar in the system. It is simply determined by the properties of that function itself, and the position of the flux balance subspace then follows from that. Okay, so it will depend in a complicated implicit way on all the parameters in the system, but not all parameters. I mean all parameters characterizing the reaction rates, but not on n bar, and of course neither on L as I send L to infinity. Okay. All right. Now, what is left open now in this picture? As you have these regions, plateau, interface, plateau, there is two characteristic points or quantities I didn't talk about yet, namely what is the position of the interface, right? So where is this located? Is this to the left or to the right? And then there is a width of the interface, a length scale, and I did not specify that yet. So L interface is also something that I haven't talked about yet. And in the following, I will explore those two questions in more detail. What I do before that is I'll take this picture of regions where you have plateau, interface, and plateau very seriously and make my system super simple, namely just being composed of two compartments, a left one and a right one. That's useful in general in a more global context. Remember those mean oscillations going back and forth between one cell pole and the other. It was clear just from the phenomenology of that oscillation that there's polar regions, right and left, and there's an interface region. So it would be desirable, if you want to understand those oscillations, to have a reduction of the complex dynamics into a polar region and an interface. And that's something I will do next week. So this reduction from a spatially extended system to a two-compartment system will be useful in many ways. So let me wipe the board and then continue from there. This is kind of the cheat sheet you need in order to follow the rest of the presentation. All right. Good. So the idea is to reduce to a two-compartment model And this is like focusing on the elementary unit of the pattern, which is an interface. So even if you have something that you saw in a movie where you have a set of patterns, mountains and valleys, the basic unit in all these patterns was an interface. So a region dividing two different compartments. Okay. So this is focusing on the interface as the elementary unit of a pattern. Okay, what's the idea? So here in this description, the way you look at the system is that you have some spatial profile m of x, and then now I would like to replace that by a two compartment system such that so you have here these two containers, here the container 1 and there the container 2, so left and right side of my one-dimensional line. In those containers I'll have concentrations for the cytosol and also for the membrane, so C1 M1 and C2 M2, and in between there's a gradient between the two values. And I will not talk about the gradients. Having those two compartments, the interface kind of shrinks to 0 in such a representation. So here in that case, the way you had exchange in the x direction is via diffusion constants and via the Laplacian that mediates this exchange. Here instead I have two containers, so this is now replaced by an exchange rate of particles from one container to the other and back. So let me write down the equations for m as an example. So dt m1 will be locally in this container just be characterized by the reactions for the two variables m1 and c1. In a similar way, if you are in the right container, the reaction terms will be just those which have the values m2 and c2. Between the two, well, you have then an exchange rate. So here we'll have, if m1 is differing from m2, or here if this is the other way around, if m1 is larger than m2, there's an exchange rate between the two, and I call this exchange rate calligraphic calligraphic d of m. Okay, these are exchange rates, and they are related to the diffusion rates once I'm fixing what the scale is I'm looking at. And I could look at the scale of the system, so I could put as the length scale, which is characteristic here, the whole system size, or I could just single out some interface in between along my long line of patterns that I have. So let me call the length scale here, which is between the two patterns, between the two compartments, just L. And then the relation between these exchange rates and the diffusion constants on those scales is essentially the diffusion constant divided by L squared. And to be precise, this is pi squared over 2L squared. And what's important here really is that this is diffusion constant divided by the length squared. Diffusion constant has units of meters squared per second. So if you divide by a length squared, you'll get a time scale, an inverse time scale. So that's a rate here, while this is a diffusion constant. All right, so that's the two-compartment model. And then now I would like to discuss that two-compartment model. And for that, well, I could write the same equations, of course, for C1 and C2. They look very similar, just with F replaced by minus F. Now let's say we look at differences in the concentrations. So delta M now is the difference in the values of the concentrations between the two compartments, M2 minus M1. And then combining those equations here, you can write an equation for delta M. And now let me put the diffusion term first. So as you put the diffusion term first, those two terms then in the end give you minus 2 times the exchange rate times delta M. And the reaction terms simply are the reaction rates at compartment 2 minus the reaction rate at compartment 1. Let me say now delta M is small, so I'm looking at small perturbations. Then you can further simplify here the right-hand side. So for delta M and delta C small, this then simply reads as the derivative of the null-line with respect to M plus the derivative of the null-line with respect to C. So you have a linear equation now, and this linear equation is an ODE. The ODE for delta M and delta C, and if you add a second equation, you'll have a set of closed equations, ODE equations, so ordinary differential equations for delta M and delta C that you can analyze. So let me analyze those equations, and for that, where do I put this? Yeah, maybe here. So let's look at the null-line again. So here I am in phase space. With M and C. And we always have these N-shaped null-lines. And I'm now looking at a point, so here, in that vicinity, and blow this up so you see what the feature here is in this region, namely that you simply have a downward slope of the null-line. And let me not put M here, but N, which is M plus C. Then this here is just saying that as I change on the horizontal line the total density of my protein mass, that the concentration of the proteins in the cytosol has to decline with increasing number of proteins in my system. That's the choice I make. That's the point I want to analyze, and I want to see what happens there. You already know what happens there, right? Because we had these geometric criteria in the general case. Here it's just in its most bare bone form where you see it very explicitly why and what happens. Okay, now let's look into the real space picture. And this real space picture is particularly simple because it just contains these two boxes. Box 1 on the left and box 2 on the right. Now let's put ourselves in a position where we start here from this fixed point value initially, right? Let's call this C star and M star, those fixed point values, and make a perturbation. So initially have some even distribution of concentration in cytosolic proteins and membrane proteins, and now let's say I move by some random fluctuation or by hand a certain amount of mass from the left box to the right box. So that means in that picture, if this here is left, so 1 and this here is 2, that I'm distributing the mass here such that in box 2 I'm moving to the right and in box 1 I'm moving to the left. So let me indicate this as this dashed line and elongate this here a little so it becomes clearer. All right, let's say this initial perturbation was as strong to get me here and at the same distance then over there. What will happen in box 1 and box 2? Well, what happens in box 1 and box 2 is determined by what the reactions want you to do. What the reactions want to do is encoded by the nullcline and by the stability of the nullcline. The choice I made is that all these local equilibria on that nullcline are actually all stable, right? And as they're all stable, if you're here on that point or here on that point, the reactive flow will pull you towards that nullcline, all right? So you will be pulled up here and down there, and if there would be no counteracting force, it would pull you all the way towards the Okay, so the first term is this one, Fm n naught divided by dm, and then minus, and I divide by dm, so I'm left with dc, minus Fc at n naught divided by dc. Well, now you should, I guess, look back in your notes, or in case you remember, this is the expression for the boundary of the set of unstable modes. So this is equal to q max squared at n naught. And now let's talk about this a little, because there's some physics here. It's not a accident that the wavelength that determines the interface is the marginal mode of a band of unstable modes. So what the physics here is, the interface in such a pattern is in a regime where it's laterally unstable. So that lateral instability drives the system and makes it spatially inhomogeneous. And the only point where this whole process can cease and you get a stationary pattern is there where the corresponding wavelength for that is at the edge of the band of unstable modes, where it doesn't grow anymore. So this is the natural length scale of the pattern. So again, you can learn something very important here. The interface length scale is determined by the edge of the band of unstable modes, evaluated for a spectrum that you determine at the intersection point of the Nalk line and the flux balance subspace in the system. And that's interesting, right? Because this here is a linear spectrum. The pattern that you get is not a linear pattern. It's the final pattern, and it has an interface. So representing that in terms of Fourier modes by a perturbation theory doesn't make sense. It's a nonlinear pattern. And still, a property of the linear spectrum determines the characteristic scale in the nonlinear pattern. And the reason is, as I said, the nonlinear pattern lives with an interface close to a Turing instability, and that's why the edge of the band of unstable modes in this Turing or mass redistribution instability determines the width. All right, so this here then determines L interaction, interface. Right, now once we have that, yeah, go ahead.
Is there such a similar relationship between the properties of the linear instability and the size of the plateau regions?
The size of the plateau regions, I'll come to that. The size of the plateau regions is more a question of how large the system actually is and what the shape of the Nalk line is. Again, it's a similar question as the one you asked. So wait a second when I draw the Nalk lines for and look at the various patterns, right? Yes?
Can one construct a similar argument for these intermediate metastable patterns and their width with
Working on, yeah. Very good question. Working on it. Talk to Fridtjof. He's the student who actually runs that project. He is at present thinking about how you could describe the process of coarsening and how the interfaces play a role and how they are moving and how they are joining with the other peaks and valleys. Yeah. But you see the point, right? This is very general, and that logic must somehow apply also to the coarsening process itself. Yeah. All right. So now let's talk about the different patterns, pattern types. So here we go. Pattern types. That may be small now, but let's try. Okay, let me first draw the pattern you already saw, namely the one where we had an infinite sized system such that the flux balance subspace cuts through like that, and the pattern then is a plateau, an interface, and a plateau from M minus to M plus. This is not necessarily L going to infinity. This type of pattern you also get if this N-shaped null-line is very pronounced, because then it doesn't really need a large system size for that point and that point here to come close to the intersection point of the null-line with the flux balance subspace. So generically, this type of pattern applies if you have an N-shaped null-line like so. Only if you make the system size very small, and that's the next point, you can make this deviate. So make L very small, and small here really means we can specify that comparable, well, let's say of the order of the interface size. Then the pattern you get and the phase space picture you have is such that now this ends somewhere in between, doesn't really go all the way to the intersection points, and for the pattern that means this more looks like a first mode, like a sine or cosine mode with one wavelength only. And you can picture that just as the case I looked at. If you make the system size small enough, looking at the spectrum, what will happen is there will only be one mode or a few modes fitting in there, and that means the patterns you get, they can't have a steep slope. They must be in some way very shallow profiles. Okay, the last case is, I guess, the more interesting case, which also applies for various biological systems people look at and where they use it. So let's say our null-line looks like so. Here we have again M and C, and for all the other ones the same. Now you have to help me, okay? Let's draw the flux balance subspace, and let's say it has some finite inclination. If you just go to a long enough system, as this curve f equal to 0 will not cut through 0, otherwise it's unphysical, there will be a point where it cuts, right? But it may be far, 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 far outside. So in that case, it's much more generic for a finite size system that the actual pattern will be on an attractor that somehow cuts or close to cuts the null-line on the left-hand side, but is not able to go all the way to the right and cut the null-line also over there. Well, how does that then look like? This means here on the left-hand side I have the first and second derivative being 0, so I'll have to have here at M minus a plateau. Then I'll go through that point. That's an inflection point, so I'll go up at some point, and then I end here with a horizontal slope at system size L, such that the interface, so L interface, is as I drew it, so you have a situation where the distance of the interface is closer to the right boundary than the width of the interface, or comparable to it. Then you don't have a plateau on the right hand side, Instead, you have a peak. Okay, so you get a peak pattern for a nullcline like so. And that means now if we want to go all the way back to the original motivation, which was polarity in yeast, right? Remember in yeast, what we looked at was a spherical cell, and there was some initial inhomogeneity, and then in the long run, there was a narrow cap here. Now take this here on a straight line, so unfold the circle. This will look like so, like a peak. Okay. Here I don't really have a peak at first, but remember I did the calculation for no flux boundary conditions, and if you would repeat the calculation for periodic boundary conditions, then of course you just fold the left part here towards the right, and you do exactly have this type of peak pattern. And that means, you know, now you can argue what is important about a reaction circuit to get a polar pattern. Do you need some modules of chemicals reacting this or the other way? Well, you may, but the essential point is that whatever reaction scheme you have, it shouldn't look like that. If you plot the nullcline, it should look like something that goes down as you increase the membrane concentration. And that's a point I think, strongly believe, is very general, that in order to understand pattern formation, what type of patterns you get, the key information to the pattern is in the geometry of phase space and the geometry of the nullcline in that space. All right. Go ahead. What's the question? Yes. Okay, so you're asking about corrections in the end, right? All these calculations are done in idealized cases, and if you here move close to the boundary, etc., then these calculations are no longer perfectly exact, right? You have a finite size system, there is some boundary effects happening, and so on and so forth. So the exact value may be different, slightly different, but in the vicinity of that. That's the point. It's like with all these asymptotic calculations, you can make them rigorous in certain limits, but once you hit some boundary situations, there's small deviations from it. Yeah. Yeah. No, it would be continuous. No, it's a curvature. So this peak here has the first derivative being 0, not the second, right? And that's the boundary condition you have when you use periodic boundary conditions. All right? Other questions? So if not, you have seen now these different patterns. And the question you can ask yourself, what happens with those patterns as you change the important control parameters in the system? So what happens as you change, well, what do we have? We can change the diffusion constants, and maybe we want to keep one of them fixed, dm fixed, and then see how the patterns evolve or whether they exist or not exist if I vary the diffusion constant for the cytosolic concentration. And then, of course, the most important, I think, parameter is still the average mass in the system, so n bar. And remember from those plots here, this n bar is determining where the homogeneous steady state lies in this flux, in this phase space. And that's what we want to do now. We want to analyze bifurcation, so qualitative changes in the patterns as we vary parameters. So that actually can be done quite easily with chalk and board or pen and paper. Again, and by now I guess you've seen this a trillion times. Let's look at the phase space, and let's draw again the null line as a function in this phase space. And let's draw in the characteristic geometric object, which is the flux balance subspace with a slope of minus dm over dc. Okay, I need this space here. All right. Now I would like to argue here, when do patterns exist and when don't they exist? And before I do so, I need to have some side calculation. So coming back to this point here, actually, I forgot this here. If you want to know the position of this interface, you can make an estimate for this position. And the estimate is very simple. You just say that you take the value of the mass here, so n minus, and you multiply by x naught, and you add to it the mass in this region, which is m plus times L minus x naught, and from then determine x naught. So x naught, as you use that simple argument, is then given by the system size n plus infinity minus n bar divided by n plus infinity minus n minus infinity. And those values of f plus, of n plus infinity and n minus infinity, they are simply these reactive phase spaces going through the landmark points at m minus and m plus. And the point I want to make here is, if you look at that equation, it determines the position of where the interface is, and you can see as you change the average initial value of the protein mass between n minus infinity and n plus infinity, you can have a pattern because the interface is within the window 0 and L. You can't have a pattern once the n bar is such that you fall outside of that window. So as soon as n bar is outside of the window, so n bar is not contained in n plus minus, n minus infinity and plus infinity, then there is no pattern anymore. All right. And that gives me the second piece of information here that I need. So those intersection points here of the flux balance subspace and the null line, they define these two boundaries. So n minus infinity and corresponding here n plus infinity, that bind the existence of patterns. So now as you draw this in a diagram where on the axis here you plot n bar, there will be a window between n minus infinity and n plus infinity where you do have patterns. Again, this is strict here in the limit of an infinite system size, because those Mesa patterns here are constructed such that I have infinite system size, and the patterns reach those landmark points only in the limit L going to infinity. So saying there exists a pattern within that window is a statement that applies in this asymptotic limit again. All right, so that's where patterns exist. Now you can ask yourself, what is the regime where you have spontaneous formation of patterns? Spontaneous means you have an initial homogeneous steady state, you add some small fluctuations, and ask when do they grow? Okay, well, what's the criterion for that? What's the criterion for lateral instability? Slope. The slope, right? So here's the slope of the narcline. I need to find the window along the narcline where the slope of the narcline is actually steeper than the slope of the flux balance subspace. So I just draw these lines here. Right? So these are parallel lines to the flux balance subspace, and that means from that point here to that point here, you have a laterally unstable regime. So let me call this n lateral minus, and this here n lateral plus. All right? And that's generically a subset. So for this n-shaped nullcline, geometrically you can't do otherwise but having these points of lateral instability inside of the band where you have possibly some patterns. And that's a geometric issue here. So this will be somewhere here, n minus, n lateral minus, n lateral plus. So you do have patterns in the whole window. In this you have a mass redistribution instability, so the system is unstable to small fluctuations, while here the system is not unstable to small fluctuation, but still has a pattern. So what does that mean? You need some large perturbations to kick the system out of the homogeneous steady state into the pattern state. So this here is a region where the system is excitable. You need a finite small perturbation to kick it out of the steady state. Now to close, let me give that axis here a meaning. Okay. So let me plot here m tilde of L minus m tilde of 0. And let's now see what this value is just by looking at those pictures on the right-hand side. Well, if I say let's say I'm in a large system and I'm in a scenario which I plotted here, then I'm here somewhere in the middle. So in that case, this value here is simply the distance between those two landmark points, m plus and m minus. So those 2 points here that I determined from the geometric construction in phase space. Yes, go ahead. Okay, the tilde means that I'm at steady state. It's the profile that the system reaches at t goes to infinity, and I wanted to distinguish that profile as t goes to infinity from the generic profile at any time t. So m tilde just says this is the steady state profile at time going to infinity. So it's this pattern. So this would be m tilde of x, and this here as well. And then the values are here m tilde L, and there m tilde 0, right? Okay, so I start out with a mesa pattern like so, and then I'm here on this guidance line that I infer simply from the geometry in phase space, which is m plus minus m minus, so the intersection points between those geometric structures. And that's how far I can go with my consideration. All I can infer still is looking at those pictures, if I'm going here to the right and to the left, so by moving my system such that this peak here moves to the right and to the left boundary, I will have deviations of the pattern from the scaffold values, and they will be such that they're drawn in some way. But in the end, you have to do this numerically, so the actual curve then looks something like that. Okay. And it doesn't go all the way. So at some threshold value, you actually jump down to the other stable branch here, which is a homogeneous steady state. All right? So what you have in the end is no patterns here and there. Then you have a regime where the system is actually bistable, or let me call it multistable, or excitable. That's equivalent here. You have two states. One is the state where you have a flat homogeneous profile. The system is spatially not ordered at all. And simultaneously, in the same parameter regime, you have a polar pattern, and there's a barrier in between. You need some finite excitation to get from that fixed point here to this fixed point. And the same true on the right-hand side. By symmetry, in between, this here is unstable, and the system flows directly to the stable pattern. All right, and I think with that I close my lecture today. And I guess you can see from what I'm talking, my main theme again and again will be that you can find a geometric interpretation of pattern formation in phase space. And this geometric interpretation in phase space is very, very useful, because otherwise, look at those equations. Do you see anything? I don't. Right? You have to numerically solve them. If you look at that picture, it makes sense now of what the system will do, determined by the characteristic geometric objects and the corresponding landmark points. In that scheme, as you will see next week, that applies very generally to more complicated systems, and is very useful as a general way of approaching pattern formation in general. Thanks for your attention. There was a question?